Last time, oh wait, before we get there, let me remind you of what we were doing last time. Okay, so before we go any further, I want you to remind me of what we talked about. So last time we were talking about the frontal lobe of the cerebral cortex, right? Okay, that's where we were. And so the boundary of the frontal lobe, if you go back, is this sulcus. What's that one called? Central sulcus, exactly. Okay, so let's talk about some functionality. Somebody give me a big picture understanding of the functionality of that most anterior portion of the frontal lobe. Problem solving, personality, complex information, reasoning, that kind of stuff. I mean, it's obviously bigger than that, but we can say executive function, right? It's like in the boss of your body. Okay, so now I want to go back here to this last gyrus before that central sulcus, which you can also, of course, see in a lateral view right here. First, tell me what that gyrus is called. Precentral gyrus. And now tell me something, some nugget about the functionality of that gyrus.
It's somatic motor. So
somatic motor control for the other side of the body. Does that make sense? Okay, good. So now we've got one more place that we learned in the frontal lobe, and that's this little area right here. And this little area was called the Broca's area or the motor speech area. Sorry, this is bothering me. I feel like I'm being interrogated. What the hell, son of a biscuit. There. I know. Do you guys need that or not?
No.
All right. If you fall asleep, I'm going to throw something at you. I've got pistachio shells right here, and they wouldn't even hurt. You'd tell me, though, wouldn't you? Okay. All right. So this right here is Broca's area. Okay. So how would you find it? What I would do if I were you is find the lateral sulcus, right? And then go just anterior to the precentral gyrus, right? And then you're going to find Wernicke's area right there. Okay, so we talked about Wernicke's area last time. We said that it was the motor speech area. So it's responsible for, if I'm telling you that if I want to communicate to you that I want to drink water, so it is responsible for producing the motor activity that communicates that to you. So I've got the idea of water in my head, but without this functioning properly, I can't write the word water or produce the word water, right? Does that make sense? So it's a motor speech area. Now, could I match water bottles to each other? Could I point to a picture of water? Yes, I could. But I can't produce the symbolism that allows me to communicate what I want with you. So I told you guys I would show you a video of this 19-year-old girl who had a stroke in the left cerebral hemisphere, and I want you to listen to the symptoms that she's talking about and tell me, other than the Wernicke's disturbance, how you would have hypothesized that she had a stroke in the left side of her brain, okay?
Is Wernicke's and Broca's the same thing?
Oh, sorry, I said Wernicke's. I'm talking about Broca's, sorry. This is Broca's aphasia. I'm going to talk about Wernicke's in a minute. This is all about Broca's. Okay, we haven't gotten to Wernicke's first. Thank you for telling me. Okay.
Okay. So what's your name?
Scott. Oh, no. Sarah Scott.
That's right. And how old are you?
I can't.
Try.
I can't.
You're 19. 19. Yeah. And what happened to you?
Stroke.
You had a stroke last year.
Yes.
And what happened? Can you remember what happened?
School and English class.
Okay.
And I book and I read it aloud. But I can't because stroke. And so I send there, and also it's the same as kind of thing as you know,
Pins and needles.
yeah,
like pins
the
and
same, and also arm as well.
leg.
And yeah.
And what happened after the stroke with your speech?
Well, I can't.
have speech problems.
Yeah.
Do you know what that's called?
Yeah. Aphasia.
Yeah, good, good.
Okay, so you can see what's happening. There's not a problem with her intellect. She still remembers her name. And she actually remembers the narrative of the story that occurred to her, but she can't come up with words dependably. So it produces this sort of halting speech pattern, which I know I want to say a word, but I can't come up with a word. And sometimes you can write things but not speak them, and some people with Broca's aphasia, it depends on how much is damaged, can't do either. There was the guy who had the worst case of Broca's aphasia that has been recorded, and look at his brain. Do you see? This is post-mortem. That whole area was destroyed. They called him the tan man because he could literally not produce any word except tan. And no matter what he was trying to say or what he was trying to communicate, he could just communicate tan, 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 tan. He could point to what he wanted to communicate, but he couldn't actually come up with the words or produce the words. So this is the motor speech area. And what she has is called Broca's aphasia. Okay, so any questions? Are we good? Okay. So, all right. So now we are ready to move from the frontal lobe back to the parietal lobes. So how do we find the location of the parietal lobes? Well, we move behind, of course, the central sulcus, right? That's the parietal lobe. Where do you stop? You stop at this parieto-occipital sulcus, but you can't see that from the outside. Keep this in mind for lab, okay? The parieto-occipital sulcus from the lateral view, you can't see it, but I want you to look now from a medial view and then realize that if you found it medially, you could follow it out laterally, okay? So can you find the parieto-occipital sulcus here? Yeah, it's really easily distinguishable from a medial view, and then you follow it out. So when you are in the parietal lobe, it's from here to here. Of course, the lateral sulcus divides the temporal lobe, so it's basically this region back here. And by the way, like I told you last time, the frontal lobe does not correspond directly with the frontal bone because it's bigger. The central sulcus is about right here, okay? So all of that is frontal lobe, and then I have parietal back to about here, right? So the frontal lobe is much bigger than the frontal bone, okay? All right, so let's talk about the parietal lobe functionality. The parietal lobe functionality, to oversimplify, is sensation. And specifically, it's somatic sensation. So here it is right here in yellow, okay? The location that you are looking at is the postcentral gyrus, okay? The name for that functionally is, listen, the somatosensory cortex. Help me break that down. What does that mean? Somatosensory cortex. Yeah, we're somatic sensations, right? And why cortex? Because it's the part of the cerebral cortex that does somatic sensations, right? So it's called the somatosensory cortex. Everybody okay with that? So now let's look at what is going on there. What is going on there is, so we looked at this last time, right? This was the amount of architecture or the surface area that gets devoted to different motor activity, and this was in the prefrontal gyrus, right? Okay, so that was motor, but now I'm going to move back to the postcentral gyrus, and I'm going to look at sensation. So do you see? Okay, so now, of course, it's not evenly distributed either, because, of course, try to feel what's going on with your elbow versus what's going on with your lips. It does not have the same amount of processing, right? Okay, so you could tell, hey, something's touching my elbow. Do I know whether it's hot or cold? Probably not, unless it's super hot or super cold, right? Do I know the texture of it really? Can I distinguish whether it's really fuzzy, right? No, I can't, okay? So the amount of processing space that you give to sensation will allow you a lot of capacity for distinguishing between sensations, for identification. So this is called the somatosensory cortex, and the somatosensory cortex is the postcentral gyrus. So what I'm saying is, if I do this, in order to be aware of it, it has to go to the postcentral gyrus on the other side of my brain. And specifically, if it was for the hand, it would be, oh, okay, right about here-ish, right? Does that make sense? Okay, so notice that you can always tell the sensory from the motor because the genitals get a distinct amount of sensory real estate and they don't get much motor real estate because you can't really do any tricks with your genitals. So this was what we looked at last time, right? This is the motor homunculus that shows you proportional amounts of the cerebral cortex devoted to those motor functions. Of course, your hands get a tremendous amount, your face, your lips, and your tongue. But now this is the motor homunculus. And the easiest way to tell is, of course, big old penis there, right? Okay? Yeah, it's a distinct amount of surface area. Now, is it only for the penis? No, of course. It's just a little difficult to distinguish the shape of a vagina on a picture like this, but everybody can recognize a penis from 10 yards. So you could draw the same one for the female with genitals, right? Okay, so that is the somatosensory cortex in the postcentral gyrus, which is in what lobe? Parietal lobe. Okay, are you starting to get it a little bit? Not as easy. No, the brain isn't easy. Okay, so now we're ready to move back to the occipital lobes. And luckily, these are relatively easy to understand the function as long as we keep it kind of simple. So with the occipital lobe, again, in order to find the boundaries of it, you start from the inside and move out, right? So you find the parieto-occipital sulcus and follow it out. Once you find it, then everything posterior to that is the occipital lobe. And the occipital lobe is not very hard because, of course, what it mostly does is vision, okay? So when you are actually seeing anything, in order to become aware of it, it actually has to go to the back of your brain in order for you to become aware of it, okay? So that's the occipital lobe. That's all you really have to know about the occipital lobe. And then we have two more lobes. This guy right out here sitting off on the side, it's called the temporal lobe, okay? And the temporal lobe, of course, sits kind of just over your ears. It's like right here. And you can't see it from a dorsal view, but you certainly can see it from a lateral view. So let's talk about what's going on in the temporal lobe. First off, the architecture. Everything sort of below the lateral sulcus is considered the temporal lobe, and it's anterior to the parieto-occipital sulcus. Okay, so this is the temporal lobe. What's going on there primarily is hearing and smell. Okay, there's a little bit more, but primarily what's going on there is hearing and smell. So if you hear something, that's easy to remember because it's like right over your ears. But of course, smell also goes there. And so if someone ends up with a lesion in that area, sometimes they will have olfactory hallucinations. So you're like, what the hell is going on? You're like, I'm pretty sure I smell sauerkraut for like the last 4 days, and I'm not eating a Reuben. How the hell is this? So, it's just the smell is just random, something that your brain is kind of like making up for you. So in addition, there's some more language over there in the temporal lobe, a little bit more of language. So I want you to think about speech and word comprehension. So, and processing, like understanding and processing language. So not so much producing, like the motor speech area, that's up here, right? But understanding and comprehending the words that you're producing or the words that somebody else is producing. So can we agree that language is symbology? It's symbolism, right? It's using a symbol, either a heard symbol or a written symbol, to produce an idea. So I can say the word apple, I can write the word apple, but they don't mean anything until I get to a certain age in which somebody puts together the idea of the red thing that you can take bites of and taste this way, with that verbal pattern, that auditory pattern, or that written pattern. So what you're going to do here is you're going to impart meanings to words here. So this is the speech comprehension area. Now, it's called the Wernicke's area, and it's only a part here. Let me show you where it is. So here's Wernicke's. So go along the lateral sulcus, close to the back, but not all the way to the parieto-occipital sulcus is the Wernicke's area. And it's kind of at the border of the temporal lobe and the parietal lobe. Usually they consider it part of the temporal, but it's kind of arbitrary where you put it. And this is called Wernicke's area, and it's called the speech comprehension area. And so if somebody has a stroke back there, then they end up with a different type of aphasia. And aphasia is a speech disturbance. So what would this type of aphasia look like? Well, it doesn't cause any problems with producing the motor activity. So I can say words, but what happens is I lose the association of the words to the meanings. So if I wanted to say to you again, I would like a drink of water, I'm looking at you and I'm saying kumquat 62 for whatever. But I think I'm communicating that I want a drink of water, but I have lost the connection with the symbols and the actual meaning, right? Could I point to water to tell you what I want? Yeah, I can point to water, right, to tell you what I want. So this is a comprehension issue. So let me show you what Wernicke's aphasia looks like, because I have Wernicke's too. This is a really old one, but that's a good one.
Where do you live?
Where do you live? You're in your live, you're up here, see? And,
Where do you live, Doc?
where do you live?
Where do you live?
Where do you live is, well, it's first around here, around here. You know?
You used to be a dentist.
Yes,
Where?
right here.
Yeah?
Rest of here, yes.
How many years were you a dentist?
How many? Holy Christmas. Oh, about 100 and, let's see, 130, about 40, no. Gosh, what number is it? One plus 5, no. It's a pretty good close to get this one, Dave. It's right over your loft, see? It's claws. It goes for about over 30, see, or 130 for down, see, in front of out for it's left straight against her, and then it comes back to the other against her 4, and then goes out for the rest.
So you see the difference with that one. So they're producing words, and sometimes they aren't actually words. They're just like, smashing syllables together. And then there's a lot of what's called echolalia, which means that you say something and I parrot it back. It doesn't mean I'm understanding what you're saying. You could tell that he wasn't quite understanding your questions. Not only could he not produce the answers, but she said, where were you a dentist, right? And he didn't understand what she meant by where were you a dentist, right? Or how long, right? So it's language comprehension, not just in produced language, but also in understood language. Go ahead.
Would this affect like the ability to do sign language?
That's a great question. I would bet that it would. I've never thought about that question before. If you find out the answer, I want you to teach me. If I find out the answer, I will teach you. I would imagine it would. Because it's just symbols with ideas, right? And you have to put symbols together with ideas. It doesn't even matter what the symbols are. But that's a great question.
It's more like lower than it is.
Yeah, I don't know. Go ahead.
So I know that he's saying the wrong thing, but does he know that he's saying the wrong thing and he just can't get it out, or does he just not understand what she's saying?
He understands what the image is, and he could, for instance, show you an apple or show you water. But he's lost the communication between at least some of the words, not all of his words. Sometimes they will hold on to some words, and the idea behind them. So he is misunderstanding her, yes, and he also is misunderstanding himself. He has lost the communication. He hasn't lost any intelligence, but it's really difficult to manifest intelligence if you can't communicate, right? So you end up having this amazingly frustrated, sort of locked in, depression, anxiety, all of that stuff goes on with both of these disorders. The first one is even slightly easier to get past because at least you know that you're not saying it correctly, but with this one you lose the capacity to understand that you're not saying it correctly. So anyway, this one's Wernicke's aphasia. I thought you guys might find those interesting.
Could he read it?
What?
Could he read it?
I don't think so. I think I looked that up before, but I don't remember. I don't think so. Okay, so that's temporal lobes. So if you are not doing this, it would be useful for you to, I know that you won't do it until after your lab practical, but doing the coloring so that you can figure out where things are, the boundaries of them. A lot of times people think that they know where they are, but then when they look at an actual image and have to identify which thing is where, they get all confused, anterior to posterior and lateral to medial. So the coloring things in here would be useful if you did them. Okay, and the last part of the cerebral cortex, or the cerebral, the cerebral cortex, the last lobe is a lobe that's really hard to imagine where it is. So, and they don't teach it very often because we actually have the least information about this one because it's really hidden. So do you see this area right here where they actually like retracted the temporal lobe from the frontal lobe, and then you've got this little chunk of cerebral cortex that's in there. So I want to show you what it looks like on a coronal section so that you will understand what you're actually seeing. So if I do a coronal section right through here, this is what it would look like. Do you see that little fold in there? That's part of the cerebral cortex too. It's called the insula. And the insula is the one that we have a little trouble understanding. It helps with smell as well. But sorry, it helps with taste. Sorry, the smell is on the temporal. Okay, so insula is deep to the lateral sulcus. You have to pull the temporal lobe back. It is your awareness of what's happening with your body. It's some of your memory, although memory is super complicated. It involves a bunch of parts of the brain. And it also has taste in it. And when people have a lesion in that, sometimes it manifests as a taste hallucination. Like all of a sudden, you are tasting, what's something horrible? You're tasting hard-boiled eggs for 16 hours, right? And they're all right for a couple minutes. We can agree, right? But for 16 hours, you're like, this is incredibly unpleasant. So you have taste hallucinations. You're not actually taking anything in, but you're hallucinating. So that's what sometimes happens with the insula, which is really hard to see. Okay, so now let's talk about the truth and the wives' tales in this whole idea of left brain versus right brain. Okay, so you've heard it before. You've heard it a million times. You might even think that you know what you are. And you're probably partially right, but let's talk about what's actually known there. So with hemisphere specialization or lateralization, what we're talking about is left cerebral hemisphere versus right cerebral hemisphere. And there is some specialization of the cerebral hemispheres. For instance, most language in 80% of us is located in the left side. That's true pretty much for almost anyone. And another 20% has both of the sides flipped, and we really don't understand that development at all yet. But what other things are located disproportionately in one side or the other, and what does this have to do with how your brain works personally? So in the left cerebral hemisphere is most things related to patterns. Okay, so can we agree that language is patterns? Yes. Mathematics, patterns. How about at least the structure of music? Is that patterns? Okay. So language, math, skills. So if you have a disorder over on this side, it can cause problems with understanding patterns. And it's also very likely to cause problems with speech. Okay. So if you are having a left cerebral hemisphere stroke, a lot of times you'll have some kind of speech disturbance. Oh, by the way, what else from that first video did you notice about what she was experiencing that told you that it might be in the left side of her brain? Yeah, she had tingling on right side of her arm and right side of her egg that she couldn't come up with a name for, right? So, the left side does patterns and speech, but there's an interesting thing about the left side. What they figured out over the last few years is your left side really, really wants to find a pattern, like so badly. It's really trying to understand the world. It's looking at all of this crap that's happening. It's like, what is the pattern? What is the pattern? I want a pattern. It wants a pattern so much that it will lie to you to make a good pattern. So if you experience this and you experience this, it's like, what would make a lot of sense? If I pretended that this occurred in the middle. I'm going to tell you that occurred, right? So you go to the store, you forget the milk. You're like, okay, I understand this pattern. You don't respect me. You went to the store, you didn't get the milk, you don't respect me. I understand the pattern. I can continue with my life. So it lies to you to make a good story. And you need to remember that your brain is trying to make you happy, but sometimes it's a codependent partner. It's like, I think this would make her happy, right? I'm going to give you some information and pretend like it actually happened. So the left cerebral hemisphere will lie to you to make a good story, to make a pattern seem like it's going to make sense of the world. Okay, so now let's talk about the right cerebral hemisphere. So the right cerebral hemisphere tends to, in 80% of us, be more specialized with, I don't know how to talk about this very well. I keep trying to figure out a good metaphor for it, but I think it's because I'm so damn left-brained I can't come up with it. So the right brain is understanding your position in space, and not just in space now, but in space in the world. like your visual spatial capacities, I suck at it, just absolutely atrociously suck at it. Your visual spatial awareness, your ability to like, so here's me. Like when I moved to Utah, people were like, oh, the grid system is great here. I had no idea what the hell they were talking about. The same address has the words west and south in it. I'm like, are you west or are you south? I have no idea what the hell you're talking about. Why don't you just tell me to turn right? Don't tell me to go toward the mountains. I came from Texas. There are mountains everywhere here. I don't know what the hell you're talking about. So I have a really hard time with that kind of like visual spatial stuff. In addition, over on that side, your creative abilities, but we're talking about visually creative abilities, right? I'm not saying that all creativity, because you can be very creative with patterns, right? You can be incredibly creative with patterns, but this is a different kind of creativity. Also, this part, your ability to recognize when someone is like giving you the stink eye, your ability to recognize expressions and also produce expressions in your face is in this side. If that is broken, you are going to have some serious social interaction problems. Also, not generating the language, but imparting emotional content to the language. So the difference with the right cerebral hemisphere will be able to tell the difference between me saying, yeah, right, and me saying, yeah, right, which are entirely different, right? Despite the fact that you are using the same symbols, the same pattern. So that's in the right cerebral hemisphere. There's also odor discrimination, usually disproportionately is on the right side than the left side. If you have a problem with the right side, a lot of times instead of having a speech problem and producing speech one way or the other, you'll start speaking in a monotone. Just absolutely flat affect and no expression in your voice. And I know some of you guys are thinking, well, I have teachers like that. They don't all have strokes in the right cerebral hemisphere. Not all of them, right? Okay, so left versus right. So what are you? Well, unless you're missing half your damn brain, you're both. But what are you good at? Well, that's generally what you completely revisit over and over again, right? So if I am incredibly skilled at producing visual art, if I'm an amazing sculptor, then I will continue to do that because I get pleasure in it and I get a lot of positive feedback from it. But I love patterns. I have loved patterns in language and patterns in science and patterns in music and patterns in mathematics. It gives me a tremendous amount of satisfaction to the point that I am like neurotic about it. I'm like, oh, I just figured out how that goes together. Oh my God, my world is complete. Over and over and over and over and over again. And it gives me a lot of pleasure. So of course, that's what I've been doing my whole life. Does this side of my brain not work? Well, it's there. I'm pretty sure it gets a little bit of blood flow. And part of it works because I can speak with emotion in my voice, right? But so I'm not either side, and neither are you. But based on your predisposition and then your reinforcement, right, you can end up doing more one of the other. But it's also societally influenced because historically speaking, go back 100 years. Did you have a lot of women who got involved in science 100 years ago? Was it because their brain didn't do science? Oh, my brain doesn't do science. No, it's because, do you ever get any social reinforcement 100 years ago for being a female scientist? No, right? And you need a little bit of social reinforcement so that the thing that you are doing is something you want to revisit, right? Some people need less of it than others. Okay, so one last thing about this. So variation between people is really common. Like I said, 20% of people have it flipped. We don't understand that. Women have less dramatic hemisphere lateralization than men, which is good if you have a stroke, because if I have a little overlap between the functionality and I have a stroke on the right side, then the left side can pick up the slack pretty easily. Women also tend to have more white matter connecting the left to the right cerebral hemispheres, so because of that, they also have less dramatic impacts of strokes and recover more quickly from strokes. So here, can you think of an activity, any activity, that causes a tremendous amount of communication between your left and your right cerebral hemispheres and requires both of them to do it well? Any idea? Music. Yes, music is the classic. So I want you to think about this because it's not a wives' tale. This one is actually true. This one has actually been confirmed by postmortem examination on people who have been composing music for most of their lives. They have a thicker thicker corpus callosum than the rest of us. So I want you to think about the ways in which music engages both halves of your brain. So first, I want you to think about reading music or listening to music, right? So when you're reading music, of course, you're taking patterns and you're making them into different kinds of patterns, which of course is a left cerebral cortex activity. Or even if you're listening, you do listen to the pattern, right? You know when the chorus and verse is, right? And you know when they flip something off or cut it off or flip something upside down right then. And your brain actually really likes it, right? It's like, I figured out the pattern, I figured out the pattern. Oh, you surprised me. This is delightful. I love the song, right? That's like half the music right there. So you surprised me in a way that I didn't predict it. And when you can predict it all, like house music, are you entertained? You're like, da, 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 da. Oh my God, stop it. Just stop it. I'm going to kill myself. So my husband's a DJ. I'm like, you do not play house music in this house. That is not allowed. So that's the left side. But now, in order to understand what the music is communicating, don't you have to be able to distinguish the emotional content of the music? Don't tell me music doesn't have emotion in it, right? So you can distinguish there are sad songs, there are really happy songs, right? Even without the words, you can tell whether it's sad or happy. So that's the emotional content. But now, if you really, really want to get it engaged, you play music. You read the music, let's talk about piano, and then you play the music. I want you to imagine what your brain has to do. Pattern, motor activity, sensory input to figuring out whether I'm doing the motor activity. Left brain right here, right brain right there, left brain this side. So you have to do the precentral gyrus and the postcentral gyrus on both sides, and you have to coordinate them with one another. And you have to listen to the feedback of the sensations that you're putting in. And then once you've got the song down, then you start working on the emotional content, right? Because you can play piano absolutely technically beautifully, and you can suck at piano, right? You're like, I don't want to listen to that ever again. So music, and early and often music training, especially when you have to read and also compose or produce the music, ends up increasing the amount of white matter connections between the left and the right cerebral hemispheres. It is phenomenal. I've been torturing my poor little boy since he was 5. He's been taking piano. He hates every blasted minute of it, every minute of it. We fight about it every single week. It's fine. But I'm still going to make him do it because, of course, he's going to support me by being really brilliant when he's older. So how many of us had to take music lessons? Keep your hand up if you fought it. You didn't fight it? A couple of you guys didn't? Oh, yeah, you go home and you tell your parents thank you. That's what you do. You're like, thanks, Mom. I'm smart because of you. Dad, too, but generally moms. I do all the driving, right? Because my husband's like, I have this important thing I need to do right here. I'm like, yeah, none of my crap's important at all. Okay, so they've done postmortems on musicians, musical composers, and you end up having a measurable difference in the thickness of the cerebral cortex. Now, am I saying you're going to get a measurable difference? No, but of course it doesn't go from 0 to measurable without getting any more fibers between it, right? So you're increasing the communication between the cerebral hemispheres, which I think is awesome. I didn't get any music training when I was a kid. I could have been 10 IQ points smarter. Thanks, Mom. Of course, we were poor, so poor people don't have music lessons. I don't know if you know that. Okay, so let's talk about deep to the cerebral cortex. Now we're going to go deep. We are going to, okay, so let's do a coronal section of the brain, okay? And so if you do a coronal section of the brain, you can see the white matter and gray matter, okay? So let's focus on the white matter for a second, and you can see it right here as well. So if you look at the white matter, here's what I want you to imagine. First of all, it initially just looks like a big blob of white matter, but what I want to tell you, remind you, is that the white matter is wiring, right? And so it's a bunch of axons, and the axons have directionality. You can't see them unless you really start dissecting out, but what you have is you have axons that are going left to right, okay? You have axons that are going anterior to posterior, posterior to anterior, that direction. And then you have axons that are going up to down, right? Like connecting the cerebral cortex to like the spinal cord. Does that make sense? Okay, so remember that when you have white matter within the central nervous system, of course it's myelinated axons, so it is wiring. So we're really not talking about processing at this point. We're talking about communicating between the processors. And when you have white matter within central nervous system, you don't call it a nerve, you call it a tract or a pathway, okay? So there are 3 different categories of tracts or pathways, and they are the one that we keep seeing, the one that goes left to right. Let's start with that one. This one right here is the biggest tract in your brain. It's called the Corpus Callosum, and it is an example of a left to right tract called a commissural tract. Commissural, that's what they're called. And for instance, this communicates things that happen over here to things that happen over here. So here's what I want to tell you. In order for me to say these two statements and a difference between them, I have to go from the left speech portions over here to the right emotional portions. So if I'm going to say, yeah, right, versus, yeah, right, that involves coming up with the patterns over here and imparting the emotional content over here. Does that make sense? Okay, so that would go, for instance, through the Corpus Callosum, which is a commissural tract. But you've got two other kinds of tracts. And the two other kinds of tracts are, okay, the ones that goes up to down, okay? So these that go from the spinal cord up to the cerebral cortex and through the other structures and back down, those are called projection tracts, which are easy to remember because they project up, right? That makes sense? Now, this is why you have the weirdness, by the way. Do you see this crossing right here? This is your wiring actually gets cross in the wiring that occurs in the brainstem. All of the stuff that comes up from this side ends up on that side, and all of the stuff that comes up from this side ends up on that side. And we don't know why this developed evolutionarily. We can see it develop embryonically. You can see how the crossing occurs. And it's way, way older than humans. We inherited it, for instance, it's true in fish, right? So it's pretty damn old as far as vertebrate evolution. And I don't know the story about why it occurred, but it's older, way older than us. And we see it consistently throughout mammalian anatomy and physiology and even before mammals, vertebrate anatomy and physiology. So this area right here is called the Decussation of Pyramids. That's what it's called. And so here's what happens. Because of the decussation of pyramids, let's talk about what happens. If I do this, right, it's going to go up my spinal cord. In the brainstem, it's going to cross over to that side, right? And so in order for me to know that it happened in my leg, it's going to go to the postcentral gyrus on that side, right? And so in order for me to respond with my right arm by doing this, right, it's going to come from the precentral gyrus, right, go down through my spinal cord, out the other side, and this is all down a projection tract out to my arm and then cause this to occur. That make sense? Okay, so this is a projection tract. Obviously, well, actually, I'll ask you that in just a second. One last tract. I don't like the way that they drew this one because it looks like it's gray matter. But what about the tract that communicates between the sides within a cerebral hemisphere? This one is called an association tract. And so an association tract has white matter fibers that go anterior to posterior, posterior to anterior within a cerebral hemisphere. So these are association tracts right here that you're seeing. So let me tell you how these work. So you're actually using them right now. So what you're doing is you're taking in visual information, which is going to the occipital lobe. But in order to figure out what the hell you're looking at, you have to go all the way to the prefrontal cortex, right? You're like, what? Figuring it out? Like, what the hell am I looking at? Oh, okay, I got it. So that's actually an association tract in action right there, okay? All right, so that's association tract. Now, logic question for you. If I told you that the spinal cord had a disproportionate amount of one of the three types of tracts, can you tell me which one it might be? Yeah, it's projection tracts. It's mostly projection tracts. Not all, but mostly projection tracts. Are we okay? Now, just so you know, if you ever end up doing neuroanatomy, every damn tract has its own individual name. So, like if you did a cross-section of the spinal cord, there's like 12 different tracts in there going up and down, right? And within the brain, there's tons of them. Oh, let me show you a cool picture. Let me show you the white matter tracts real quick. Just hold on to that for a second. I forgot to bring this picture up, and it's really, really cool. Oh, did I not? Maybe I forgot to save it. Just hold on for a second. Maybe I'll find it. That's my metaphor for the brain. Oh, damn it. I think I forgot to save it. I'll show it to you guys next time. Okay. So they actually did a 3D model that shows you the white matter tracts, and it just looks like this big spidery flower within the brain. So they took off all of the gray matter, and you can just see the tracts in the brain. So I'll show it to you guys next time. Okay, so last little bit for today. is this concept. And this concept is, let's go back to our coronal section. Okay, and now let's talk about the rest of the gray matter in the brain. Do you see it? Okay, so we did the cerebral cortex and then the white matter, and now we run into this gray matter. And so it's such a struggle to figure out how to address this stuff. But what is in there are ganglia. I'm sorry, nuclei. They used to call them ganglia. They call them cerebral nuclei, or sometimes it's even better to just call them subcortical nuclei because they're below the cortex. So do you see them? Well, first of all, you can relax a little bit because I don't have you know them individually, but here they are. So just look at this with me. So this guy right here and all three of these are these subcortical nuclei. This guy right here is going to be the thalamus, and that's actually different. So how do I describe the location of the subcortical nuclei? This was the best I could come up with. They are internal clusters of paired gray matter deep within the brain. They seem to be clustered below the lateral ventricles, medial to the insula, and lateral to the thalamus. So let's find that visually so that you can figure out what the hell I'm talking about. So kind of next to the lateral ventricles, which is where that is, right? And this is the insula, right? So they're medial to the insula, and they're kind of lateral to the thalamus. Do you see where they are? Okay, so what the hell is going on in those? Remember when we were talking last time about the fact that your brainstem does life-sustaining, and then these are like evolutionarily advantageous functions? So like, you know, emotion and that kind of stuff is in there. So it's really hard to summarize, but let me just give you a big picture understanding of what the heck these do, and I won't have you learn them individually. So they're starting and stopping voluntary skeletal movement, and they are a whole bunch of your emotions. I didn't put the emotions in there. So the whole bunch of the emotions as well are in there. So you don't have to, I'm not going to test you over this, but let me tell you that like addiction is in there, right? Rage is in there. That kind of stuff is all in there as well. The thing that we know about, the thing that's easier to assess than addiction and rage is that these are responsible for not doing your skeletal movement, but initiating your movement of activity. And the reason that we know that is because one of those goes bad in Parkinson's disease, and you start to lose the ability to start and stop your skeletal movement voluntarily. And Tourette syndrome. Tourette syndrome, in which you have these tics, these twitches, these outbursts of motor activity that you actually weren't trying to start, and you have trouble actually tamping them down, that occurs in there as well. Okay, so what are you responsible for with those? And then I'll let you guys go. By the time you get ready to study this, you need to know that they are gray matter, and you need to be able to find them on a coronal section. Okay, do you need to be able to label them individually? Because there's the caudate nucleus, the putamen, the globus palatus, the lentiform, the claustrum, the amygdala. Have you guys heard of amygdala, rage? The amygdala is in there as well. So you need to be able to find them, okay? But not individually. Just, okay, this is a cerebral nucleus, right? Okay, all right, so I will see you guys on Monday for your test.